In this video, we look at the polyatomic ion phosphate and figuring out the charge on it. This substance, in its neutral form, does not exist, but forms compounds with the charge -3. So how do we figure this charge on it out? We'll look at it from two ways. First, consider the compounds that phosphate forms. Calcium phosphate. Calcium has an oxidation number of +2, and there are 3 of them over here. So calcium is contributing +6 oxidation number to the compound. So in order for calcium phosphate to be a neutral compound, this part of the compound should contribute a total of -6 oxidation number. Now there are 2 of them over here, and so phosphate should have an oxidation number of -3 in order for this compound to be neutral. Now if you take a compound like aluminium phosphate, which is a neutral compound, aluminium has an oxidation number of +3, and so contributing to +3 oxidation number of the whole compound. So in order for this compound to be a neutral compound, this part of the compound, the anion, should contribute or have an oxidation number of -3 in order for this compound, aluminium phosphate, to be a neutral compound. And so from the compounds that the phosphate forms, one is able to understand why the charge on phosphate is -3. The other way is by looking at the Lewis structure of phosphate. Now, to do that would require to know the total number of valence shell electrons that both phosphorus and oxygen provide binding together. Now, phosphorus is in group 15 or group 5A and has 5 valence shell electrons. So phosphorus provides 5 valence shell electrons. Now, oxygen is in group 16 or group 6A on the periodic table and has 6 valence shell electrons. There are 4 of them. So we are going to have 4 atoms of oxygen, each providing 6 electrons. Then 3 electrons gained when it combines with a cation. So in total, there are going to be 32 electrons that will be involved in bonding. So let's try to draw the Lewis structure of phosphate. So this is phosphorus. It provides 5 electrons. Now, phosphorus can gain 3 electrons to achieve the octet rule and become stable. It can also lose these 5 electrons on its valence shell and also become stable. When phosphorus goes into bonding with oxygen, which has a higher electronegativity value, then phosphorus would prefer to have all its 5 electrons involved in the bonding. And so this is oxygen. There are 4 of them. So now we're going to add up to 32. So we already have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So this structure can be redrawn as So here we have 3 phosphorus oxygen single bond and 1 phosphorus oxygen double bond. And so now we need to determine the formal charge on each of the 5 atoms over here. So the formal charge on each of the atoms equals the valence shell electrons of each of the atoms minus the non-bonding electrons on the atom minus the bonding electrons of the atom over 2. So if we take this atom, for example, the valence shell electrons of oxygen is 6. The non-bonding electrons are 6. This, and this. Then the bonding electrons are these 2. And so we have 2 over 2. And so the formal charge on this oxygen atom is -1. We have the same electron arrangement on this oxygen atom too. We have -1. It's the same oxygen, is the same arrangement of electrons over here. It also have a formal charge on this as -1. Now, what about this oxygen atom? Now, for this oxygen atom, the valence shell electrons for oxygen atom remains 6. Now, the non-bonding electrons are this and that, so they are 4. Then the bonding electrons is also 4. So we have 4 over 2 and we have 0. So the formal charge on this oxygen atom is 0. Now for phosphorus, the non-bonding electrons is 0 because all the electrons are involved in the bonding. So we don't have any non-bonding electrons for phosphorus. And we have bonding electrons 2, 4, 6, and 4 here. So we have a total of 10 bonding electrons for phosphorus divided by 2. So we're going to have the formal charge on phosphorus as 0. So for this molecule over here, the net charge on this molecule is -3. Now you should remember that this double bond over here, it can be here, it can be here, and it can also be here because of resonance effect. Now let's consider a situation where there is a break in this double bond and repositions itself over here. When it so happens, we are going to have this. Which means that we're going to have the formal charge on oxygen as -1, here as -1, here as -1, and here as -1. And the formal charge on phosphorus will now become +1. In that case, the valence shell electrons of phosphorus remains 5. The non-bonding electrons remain 0 because all are involved bonding to one oxygen atom or the other. But the bonding electrons will now be 8. So we are going to have 8 over 2, and that is going to give us 5 minus 4, and that is going to be +1. So when it so happens, still the net charge on this molecule will still be -3. Of -3 atom. Now let me quickly show the electrons around the atoms. Now, if we are to consider these two Lewis structures, which one is more stable? Both of them are acceptable as Lewis structures for phosphate, but which one is more stable? Now, this one is more stable. Whenever we have two or more structures or Lewis structures for a particular polyatomic ion, for a particular molecule, the one with less separation of charges is considered as the most stable. So this Lewis structure of phosphate to my left has less separation of charges compared to this one, even though both of them have the same net charge of -3 on the molecule. But this one on my right has more separation of charges compared to this one. So phosphate in this Lewis structure is more stable than this one to my right here. So this explains why the charge on the polyatomic ion phosphate is -3 using the Lewis structure explanation. So this is the end of my video. Thank you very much for watching, but keep watching.